Good morning. Today we'd like to continue our physics class. Today we will discuss about the magnetic fields and forces. Okay. The big questions in this chapter is what produce a magnetic field. So we can produce a magnetic field commonly by using two ways. The first, we can use the electromagnetic, and then the second, we can use a permanent magnet. So the electromagnet is if we begin moving electrically charged particles like this one, we can this is the like the silica, and then if we want to attract them in metal like this one, so we just uh, put or connect this metal to the electricity, and then we make like a circular path in the metal, so we can produce the electromagnet. So it will like a magnet permanent. It will like a magnet, so it can attract the the material in low material over there. So we can like attract a metal and also still a steel mill like in the picture. And the second, we can produce a magnet by using magnetic fields or B. Magnetic is the notation of magnetic field is a B. We have discussed before the midterm test. So we can also, this is the first one. The second one is we can use a permanent magnet. And there are three kind of permanent magnet: ferromagnetic, strong magnetic fields, paramagnetic, and diamagnetic. Paramagnetic is, yes, it's not as strong, but this material is contain magnetic fields. And then the third one is diamagnetic. The first one is ferromagnetic. So this one. This is the very strong magnetic, and the second is paramagnetic, and then the third is diamagnetic. Okay, this is the three kind of material in permanent magnet to produce a magnetic field. So this one is definition of the B, or the B is the magnetic field. This is magnetic field. So the electric field we talked before, E, and also the electric force, or Fe. So the electric field is E is equal to electric force per key. Key is a charge. So it is a column. So the electric field is the electric force per key. And the magnetic field, or B, and the magnetic force has a relationship like this one. This is the magnetic force, or Fb. So the key is this is the charge, and this is the velocity of charge. And this is the magnetic field. So this is the relationship between the Fb and also the magnetic field. So key V cross B, we can get the magnetic field. And the magnitude of Fb is key Vb sin theta. So this is the magnitude of Fb. So how to determine the direction of the B? We can show like in the picture. If we have the V here, and this is the B, so we can see this is the V in the second. Okay, here I erase this one. Okay, this part, this is the V cross B. V is the velocity of charge and B is magnetic fields. So V cross B is not similar to B cross V, so you have to carefully check the equations. This is in this equation is a V cross B. So if we have the direction of velocity of charge V like this one, this is the first one, we put our finger in the V, and then this is the direction of the B. So we move from the direction to V to direction to B. So the mother finger is the direction of the V. It's like this one. Yeah, this is the direction of the force of magnetic, and this is the force on positive particle, and the force of negative particle is on opposite direction with the positive particle. So this is the FB for the positive particle, and the below like this one, this is the FB for negative particle. Okay, so you can use this direction. Though the first you put your finger in the direction of the V, and then you move to direction to the B, and the mother finger is the direction of the FB, and this direction is the positive for the positive particle, and the negative particle is opposite direction like the picture number E. Okay, so the magnitude of the B is because the FB is key dot V cross B, right? So the B is equal to FB per key V, like this one. And the SI unit for B is the Tesla. 1 Tesla is 1 Newton per coulomb per second meter. And non-unit SI is Gauss. 1 Tesla is 10.4 Gauss. So this is some approximate magnetic fields you can see. And this is the another picture. The figure shows three situations in which a charged particle with velocity v travel through a uniform magnetic B. In each situation, what is the direction of magnetic force Fb of the particle? So, the first we have to put our finger in the V, okay, and then after we move to the B, and the V is X negative, B is Y negative, yeah. So you have to use this one. So the direction of the mother finger is the A is Z direction, yeah, Z negative, yeah, Z not Z positive but Z negative. This is the Z negative. Oh, Z positive, yeah. Z positive. Z positive. Yeah. So you have put your finger in V and then move to the B, so the mother finger is the Z positive. So this is the FB for the positive charge. And then the second, the V is in Y negative, and then B in Z negative. So the FB is this one. So this is the FB, and this is the FB. So FB is X positive. Okay. Okay, and it's similar to the charts. If we have the permanent magnet like this one, the permanent magnet has two poles, the north pole and south pole. So the direction of the magnetic field line is coming from the north pole to the south pole like this one. So this is the direction of magnetic fields. So if the magnetic field lines is far like this one, so like in this way, this is the far between the magnetic field. So this means that the B or magnetic field is weak, is weak, it's not very strong. But if we have the magnetic fields like this one, is near between magnetic fields line, so it means that the magnetic field is strong. So this is the weak magnetic field, and this is the strong magnetic field. So this is the direction between the north pole and south pole for the magnetic fields line. This is the horseshoe magnet, so the direction like this one, and this is the shape magnet. Okay, this is the sample problem. A uniform magnetic field B with the magnitude of 1.2 millitesla is directed vertically upward throughout the volume of the laboratory chamber, like in this one. So the V is directed vertically upward. So this is the V. And proton with the kinetic energy 5.3 mega electron volt enters the chambers, moving horizontally from south to north. Okay, so this is the path of the proton. So this is the path of the proton. What magnetic deflecting force acts on the proton as it enters the chambers? The proton mass is 1.67 across 10⁻⁻27 kilogram. So we have the magnetic fields B, and the magnetic fields B is the dot. So it means that the magnetic fields is out of the paper, yeah. So the out of the paper. So this is the V is vertically and B is out of the paper. So the direction of FB is like this one. Yeah, it's like the V in Y positive and B is Z positive. So direction of the F is X positive. Yeah, you can use your finger to check the direction of the FB. This direction is X positive. Okay. So the first, because of the question is what magnetic deflecting force. So the question is what is the FB? So the FB, the equation at the FB is KF KVB sin theta. So we have the key because this is the charge, the proton charge, and we have the B. This is the B, and the proton, the key of proton is 1.6, 10⁻⁻19 coulomb. But the phi is not, we have to calculate the phi first. And in the question, they show the kinetic energy of 5.3 mega electron volt. So by using this kinetic energy, we can calculate the phi like in the slide. The phi is equal to square of 2k per m. So the 2k is 2, this is the kinetic 5.3 mega electron volt, and don't forget to put the charge here because this is the 5.3 mega electron volt. So we have to multiply by the E is this one point yeah, oh yeah, 1.6 cross 10⁻13 joule mega electron volt. This is the charge of the proton. And then the m is the proton mass, 1.67 cross 10⁻27 kilograms. So we can get the V is 3.2 cross 10.7 meter per second. So if after we find the V, we can use this equation. So the V, Fb is key, V b sin theta. So we put the key 1.6 cross 10⁻19 coulomb, and then V here, and then the B, the B 1.2 millitesla, and this is sin 90 degree is the angle between the V and the B, and we know that the V is vertical like this one, and the B is in Z positive. So the angle between the V and the B is 90 degrees. So we can use this one and the sin 90 degree. So we can get the FB is this one, 6.1 cross 10⁻50 Newton. And so it is a modern version of G.G. Thomson apparatus for measuring the ratio of mass to charge for the electrons. So here, if we have this device like this one, so this device is useful for measure the ratio of mass between the charges. So you can see that the important part of this device is this one. We have the E, electric fields, and also the B. If we connect the filament here with the voltage here, so the charge will move from this filament to the spot of light like this one. So it will be move across this important part of the device that contain of the electric fields and also the magnetic fields. So if we want the charge move from the original part in filament to the spot of light, so the electric force and magnetic force must be equal. So the electric force must be equal to the magnetic force. So Fe is equal to Fb. So the Fe is equal to key E, and Fb is key Vb sin 90 degree. Also is similar to key Vb. So we can neglect the key, so we can get that the V is equal to E per B. E is equal to electric fields and B is magnetic field. So we can, if we inject the electric field in one situation, or in we can control it, and also we can control the magnetic fields. So we can check the velocity of the charge in this device. Okay, it's like, so if we make this important part, we make a large just like this ones. So this is the I is we can see this is like the key, because the current is the charge, is the movement of the charge. So this is the current and this is the key, and if the current is injected to this device, like this one, this device has the magnetic fields in the cross direction. It means that this in yeah, into the paper. So it's like this one. So we connect the device to the positive and negative voltage, like this one. This is the positive and negative voltage. So we can create the E, and then the currents move inside this device. So the direction of the current is opposite direction with the charge. So this is the I. The direction of I is to the bottom of the device, but the direction, the velocity of the charge is in opposite direction, like this one. So this is the VD. Yeah, for the negative charge. And the VD, if we didn't connect the device with the positive and negative, and it also means that there is no electric fields in this device. There is no electric fields. So we can see that the direction of the FB here, so this is the V is vertical direction, F and B is the inside the paper. So the force of the B is in x positive, like this one. So the charge will bend to the positive direction, like this one. This is the bending of the charge. The movement will is like this one. This is not a vertical, pure vertical, but because of there is a magnetic force, so the direction of the charge will bend to the x positive, like this one. So if we want to make a movement of the charge in vertical direction, so we have to put the strong electric fields that create the electric force in opposite direction with FB. So it's like make a balance here. So the FE must be equal to FB. So there is no the charge in x positive or x negative. So the movement of the charge in vertical direction. And also if we use the positive charge here, so the movement of the charge will also in vertical direction if the FE is equal to the FB. So this is this device. We make a larger situation of this part in here. So we can see that the magnitudes of the potential difference phi is E dot T, where E is electric field and D is the distance between the positive voltage and negative voltage, like this one. This is the D. So we can calculate the V. Okay, so this is another situations. Yeah. If we only put the magnetic field, so the direction of the charge inside the device will depends on the direction of the FB. But if we put the strong electric fields here, so we can create the balance force in the device. So the FB is equal to FE. So the movement of the charge inside the device will will move vertically or horizontally, depends on the position of the device. And another, we can also use, if we put the charge in some material, that in this material we only has the magnetic field, so the electron will make a circular in the chamber, so the movement of the particle will be circular like this one, and the circular movement of the particle will create the another F, is m v square per r. So it's similar if the movement of the charge in similar ways like this one. So this is, it means that this is not like a small position or in biggest position like this one. So the position of the charge, the movement of charge, like in stable circular part like this one. So it means that the circular motion force is equal to the magnetic field force. So we can use this one, this equation, Q V B is equal to m v squared per r. So we can neglect the v like this one. So we can calculate, like if we want to measure the m, the mass of the charge, or the velocity of the charge by using this equation, we can use these equations. Okay. And the magnetic force on a current carrying wire. So if we have the magnetic fields like this one, this is the P, and the direction of magnetic fields is outside of the paper, because this is the dot like this one. So the first, there is no current here. If we apply the current in the wiring, so the magnetic fields will have the magnetic force, so it will be bend the wiring, because of the wiring contain the wire. So the magnetic field is perpendicular to the current. Q is equal to IT is equal to I L per VD, and the VB is equal to Q VB sin theta. So if we put the key by using the IL per VD, so we can use we can get this equation, IL per VD dot VD B sin 90 degree. So we can neglect the VD, so ILB, so the FB is IL cross the B. So this is the magnetic force on a current carrying wire. So if we have the currents in the wire, inside the wire, in around the magnetic fields, so the magnetic field will create the magnetic force by this magnitude. Okay, and then this phenomena also we can use in electric motor like this one. So if we have the permanent magnet and north pole and south pole like this one, and we have the wiring like this one, this is contain the current. So it's like this one. So we have magnetic fields and we have the current inside the wire. So it'll create the F here and also F here in opposite direction. So the rectangular loop of the wire will move like a circular. So it will create another force. So it used in electric motor. So we can see that like this one. So this is we explain this equation here. So this is the circular loop here. So because of the magnetic field create the F here positive and this is negative F, so it will be creates the torsi. So the torsi is due to the force of F1 F3, so it's like this one. So the total torsi is this is the F1 and this is the F3, so we can get the total torsi by I A B sin theta. I is the currents, A is this one, this is the IA, and this is the B, and big B is the magnetic field sin theta. Okay, so this is how the magnetic fields will create a magnetic force to make another movement of the motor. So we have to exercise. I will discuss it later in another video. Okay. Good morning.